so imagine this. You're at the bar, right? You've got your cold beer. You've got some salty peanuts.
Classic combo.
You toss a few of those peanuts into your beer, and suddenly...
It's the party.
They're not just sinking to the bottom. They're putting on a show.
The mysterious case of the dancing peanuts.
Exactly. And today we are diving into the surprisingly complex physics behind this pub phenomenon.
You know, most people wouldn't look twice at their beer nuts doing a little jig.
Right.
But it actually perfectly illustrates some really cool scientific principles.
Absolutely. So we've got this paper here by Pereira and the team, and they went all in on this. High-speed cameras, the works. What they found is that this peanut dance is actually a whole cycle, like a series of steps.
A whole choreographed routine.
Okay, so what's Act 1 in our little peanut ballet?
Well, it starts pretty simply. Peanuts, denser than beer.
Makes sense.
So naturally, they sink. That's our opening scene.
Yeah.
Peanut takes a plunge to the bottom of the glass.
So far, so good. But then what? How do we go from sunken snack to dance floor sensation?
Okay, so here's where things get interesting. That peanut just sitting down there, it's not giving up. You see, the surface of a peanut, all its little nooks and crannies, it's actually the perfect place for bubbles to form.
Hold on, are you saying my glass is jealous of a peanut's ability to make bubbles?
In a way, yeah. It's all about something called contact angles.
Okay, getting a little technical here.
Basically, the beer, or the CO2 in the beer, it wants to make bubbles, right? And it much prefers to do that on surfaces that have lots of little imperfections.
So like the rougher the better.
Exactly. A peanut surface. Way more of these ideal nucleation sites than your smooth glass.
So the peanut's like a bubble magnet.
Exactly.
Then what happens? Do they just like hang out?
Oh, these bubbles have got bigger plans. They start to form, attach themselves to the peanut.
Little peanut life rafts.
And as more and more bubbles gather, something really cool happens.
Okay, I can't take the suspense. This is where the peanut starts defying gravity, right?
You got it. See, those bubbles, they're full of gas, which is way less dense than the beer. And as they cluster around the peanut, they're increasing its buoyancy. Think of it like attaching tiny balloons to a small weight.
I'm picturing it.
Eventually, that upward force from the bubbles, it gets strong enough to overcome the downward pull of gravity.
It's like a tiny game of tug-of-war, and the bubbles are winning.
Exactly. Now, here's the catch. Those bubbles can't just be any size.
Well, there's got to be rules to the game.
Pereira's research, they found a magic number. The bubbles need to reach a radius of at least 1.34 millimeters.
1.34 millimeters. Incredibly specific. These scientists really were paying attention. But why that size?
It's all about the balance of forces. 1.34 millimeters, that's the tipping point.
Tipping point 4.
That's where the buoyant force from those bubbles finally beats out the peanut's weight.
Wow. So the bubbles hit that magic size, and boom, peanut's off to the races, heading for the surface. So our peanut is living it up, riding high on its bubble elevator.
But like all good rides, gotta come back down eventually, right?
Party's over. What happened?
Well, think about it. The peanut hits the surface.
Yeah.
Whole new world up there. Pressure change. Those bubbles, they're fragile. Some of them, they just can't handle it. They burst right there at the surface.
Oof. Gone. Peanut's ride is over.
And it gets worse. Now the peanut's bobbing around up there.
Right. Less bubbles holding it up.
Exactly. And that movement, even though it seems random, makes even more bubbles detach.
Oh no, losing its grip. So what happens? Peanut sinks again.
Yep. Density takes over. Back to the bottom of the glass.
Our little dancer tuckered out.
Not so fast. This is where it gets really cool. As long as there's enough CO2 left in the beer,
there's still some fizz left in our system.
The cycle starts all over again. New bubbles, they form on the peanut, latch on.
Back for round 2.
They hit that magic 1.34 millimeters.
That magic number.
Up it goes again.
Like a never-ending dance party, at least until the beer runs out.
Exactly. And that's a key takeaway here, you know?
Oh.
This isn't really just about peanuts and beer. It's about forces. Gravity, buoyancy, surface tension, they're happening all around us constantly.
Okay, so cool, but it's still peanuts in a beer. Why should I care about this dance? What's the big deal?
That's what I love about science. Even something so simple.
Right.
It can actually teach us about huge real-world stuff.
Like what? Give me an example.
Think about mining.
Okay.
Ever heard of froth flotation?
Can't say I have. Sounds bubbly.
It is. It's how they separate valuable minerals from ore. And guess what? The idea. Super similar to our dancing peanut.
Wait, are you saying miners are using like giant vats of beer to find gold?
Not beer exactly, but same principle. Big tanks, water, ground up ore, and chemicals that make a lot of bubbles. And those bubbles, they attach to certain minerals, their surface, just like with the peanuts and the beer.
No way. So there's like the bubbles are what, mineral magnets?
Exactly. They become buoyant, float to the top with that mineral,
And then,
skim them right off. Super efficient way to separate the good stuff from the waste.
wow. Never would have thought that a peanut in my beer could explain, like, actual mining.
And there's more. Remember how we talked about the size of those bubbles being so important?
Yeah, the magic number.
Right. Well, that matters in other fields, too. Designing new materials, lightweight plastics, super strong ceramics. Scientists are messing with the size of bubbles.
Really?
Oh, yeah. At a microscopic level. It's how they get those materials to have the exact properties they want.
So those tiny bubbles, they're like building blocks.
Kind of. You control the bubbles, you control the material, strength, flexibility, even how it conducts heat or electricity.
It's wild, right? These tiny bubbles on a peanut.
Having these huge impacts.
Yeah. Makes you think, what other weird connections are out there?
Right. And that's what's so cool about science, you know? Those unexpected links.
Totally.
Take geology, for example.
Okay.
Sometimes they find really dense minerals in layers where they shouldn't be based on their weight.
So, like, heavier stuff ended up on top of lighter stuff.
Exactly.
How'd they get up there? Did they, like, take notes from the peanut?
Kinda. So, millions of years ago, picture this, these rock layers are forming, right? It's all molten material. And these minerals, they probably got stuck to bubbles rising up through that molten goop. Bubbles acted like little rafts, carrying the minerals upwards.
No way.
And then, over time, everything cooled, solidified.
Trapped the minerals in place.
Exactly. Peanut dance, but on a geological timescale.
That's insane. I'm seeing dancing peanuts everywhere now.
That's the beauty of a curious mind, right? You start seeing the connections.
Like the universe is sending us secret messages. Through beer.
Why not? But seriously, this is what it's all about.
What, getting a beer with a scientist?
Well, that too. But no, just observing. Paying attention. You never know what everyday thing will unlock some huge insight.
This has been amazing. Who knew peanuts and beer could be so deep?
Right. Science is everywhere. So next time you're at the bar, take a closer look at those peanuts. It's a whole little world in your glass.
The whole little universe. This was fantastic. Thanks for joining us for this deep dive.
Anytime.
And to everyone listening, keep those questions coming. You never know what mystery we'll tackle next. Until then, cheers.